When your experiments behave and give you a nice high-resolution crystal dataset, building and refining the matching model is a straightforward and mostly automated process these days. If things don't work out quite so well and your best crystals only diffract at 3 angstroms or worse, the process is still quite challenging. A big part of the problem here is that most crystallographic model building tools were built with those high-resolution datasets in mind and struggle when the map no longer gives the position of each atom. I developed the toolset I'm about to demonstrate specifically to improve how we work with low-resolution structures. I call it Interactive Molecular Dynamics Flexible Fitting, or iMDFF. For my demonstration, I've chosen the 3.5 angstrom structure of chicken transferrin, protein databank ID 1RYX, first published in 2003. There's no specific reason for this choice other than the fact that, like most low-resolution structures from this era, it hasn't stood the test of time very well. I'm looking at it for the first time and have no idea what I'll find, so let's have a look. Before starting, let's just have a quick look through the Ramachandran plot to get an idea of the state of the backbone. The red contour is a standard 0.05% cutoff, and we can see we have a very large number of outliers. The first thing to do is a simple equilibration of the structure to relax it into the map as much as possible. The simulation for this is actually already initialized and waiting, so all I have to do is click Go. We'll just keep watching this in Ramachandran space for a while as it first runs a 100-step energy minimization, then rattles around at 100 Kelvin. We see that most of the outliers clear up more or less immediately, leaving us with just a few dozen more serious cases to deal with. While we're waiting for that, I'll give you a few more details of the simulation. It's running under implicit solvent conditions in the CUDA build of NAMD 2.11 Beta 2 on a 5-year-old Xeon workstation aided by a GTX Titan GPU kindly donated by NVIDIA. The Ramachandran plot is being updated every 5 time steps. As well as this machine, I also run this on a 2014 model gaming laptop equipped with a GTX 980M GPU with excellent performance. Okay, now that's settled nicely, I'm going to stop the current simulation and commit the coordinates back to my master structure. And here's where the real fun begins. The sorted lists you see in the window at the top right are the current Ramachandran outliers, and they aren't there just for information. Selecting one of them allows me to quickly set up a much more targeted, interactive simulation to investigate and hopefully fix it. Let me talk you through what you're seeing here. The atoms displayed in the thicker representation are the ones that will actually be mobile in this simulation. The thinner ones are present in the simulation but fixed in space to keep the mobile atoms under control. Everything outside of this region is excluded, making for a very lightweight and therefore fast simulation. The blue wireframe is the unsharpened electron density map contoured at 1 sigma. I also have present a sharpened density map contoured at 1.5 sigma, and a difference map contoured at plus or minus 3 sigma, but since these initial maps are of rather low quality, they aren't actually showing up here. The yellow right-pointing cone is the internal representation of my haptic interface, which I'll be using extensively throughout. This tool allows me to effectively reach into the simulation, grab and pull any atom, and have the simulation respond accordingly while I feel it pulling back at me. This makes the remodeling process highly responsive and intuitive, and allows me to rapidly explore a wide range of conformations to find those that are both consistent with the density and structurally reasonable. To give an extra level of real-time feedback, I've mapped the status of each residue on the Ramachandran plot onto the color of its alpha carbon atom. Outliers are colored in red, those in allowed regions are white, and those in preferred regions are blue. Removing the need to regularly stop and check progress against the traditional plot saves an enormous amount of time. At this stage, we're not looking for perfection, but simply to give the structure a quick once-over to clear up the worst of the issues before generating some improved maps. I'll just speed up the playback for a bit. Here's a good example of what turned out to be a common problem with this structure. This flexible loop has been threaded through density that clearly doesn't belong to it, and turns out to come from a symmetry mate. Later we'll run around with the surrounding symmetry partners explicitly included to really clear up these problems, but for now I'll just move it clear as much as possible. My core philosophy in the design of this package is to do away with simple rigid body motions as much as possible, to make the modelling experience feel as close as possible to working with a real-world physical object. Here's one example where direct manipulation of coordinates remains a necessary evil. There's been a particularly bad steric clash here, which has left the backbone threaded through the ring of a tryptophan side chain. Clearly this can't be fixed within the simulation, so we'll drop back to our static main molecule and simply move side chain atoms until they're all on one side of the backbone. Don't worry about mangling the geometry, this is easily fixed with a quick energy minimization. This seems as good a time as any to stop and run a reciprocal space refinement to generate a new set of maps. I'm going to do this in a few steps. The first thing I'll do is run a b-factor only refinement with coordinates fixed to provide a model with individual b-factors from which I can derive a set of TLS groups. I'll then throw out those individual b-factors and run a restrained coordinate refinement with a TLS only b-factor model. I find that in low resolution structures this gives maps that are far more honest in terms of revealing errors. Here we are post-refinement, and we're already at a state which would place this structure in the top 10% of similar resolution structures in the protein data bank. There's still a lot more room for improvement though. Here's a good opportunity to demonstrate one of my newer features. If we pause the simulation, we can access a rotamer library whose behavior at first glance looks identical to that of any other package. The key difference here is that this is only a preview. The coordinate changes we're making are ignored by the simulation. Instead, once we've decided on a particular rotamer, this will be set as a target in dihedral space, and forces will be applied to guide the sidechain towards that conformation. I'm still tuning the force constants for this, but in general this should not be necessarily expected to get the sidechain there on its own, but rather to act as a guide to supplement manual interactions. Once it's in the chosen conformation, we can release these extra forces and let it settle naturally into the map. The next 6 minutes or so shows more of the same tinkering, leading up to another stop to re-refine and regenerate new maps. Feel free to watch along if you like, but if you get bored, just skip ahead to the 15-minute mark. So we've further cleaned up a bunch of smaller problems, and in particular those clashing loops. But in order to really handle these, we want the symmetry partners to be physically present. In future, I want the symmetry operations to be handled within the iMDF environment, but at present I just build the higher order complex of the asymmetric unit with its contacting symmetry mates in Chimera, and import it into iMDFF as a new construct. To cut down on clutter, only those parts that are actually involved in simulations will be shown. We'll run another quick low temperature equilibration to settle into the new maps. Then it's time for the final detailed cleanups. While reliance on indicators like the Ramachandran plot can help you find and fix a great many errors, it's always a good idea to run a visual check over the whole structure to find and fix any errors that don't stand out obviously on charts. I find that mobilizing stretches of 50 to 100 residues at a time, along with directly contacting residues, is generally workable. It's fast enough so that I can manually fix most small-scale errors on the spot, while I can always stop and create a more localized simulation to handle more challenging problems. To work all the way through this 683 residue structure like this takes the better part of an hour, so I'll spare you the details and skip ahead. The final segment coming up was recorded on my laptop at home, so forgive me the slight change in format. Here's an interesting feature I came across during my detailed check, an asparagine residue with a significant blob hanging off it. The sequence here is asparagine arginine threonine, and this is an extracellular protein. Sure enough, UniProt lists this residue as glycosylated, so let's add the N-acetylglucosamine. So here's the upshot. I chose this structure essentially at random from the bottom decile of 3 to 4 angstrom structures and downloaded it for the first time at approximately 10 AM. By the evening of the same day, having spent roughly 3 hours of personal time on it, interspersed with automated reciprocal space refinement, using iMDFF I have improved it to amongst the very highest quality structures in the protein databank for this resolution range. While my approach is by no means a magic bullet and has significant scope for further improvement, I hope I have made it clear that it is a valuable new addition to the structural biology toolbox. If you wish to learn more about this method and its applications, or get it up and running for yourself, please feel free to contact me at the email address below. Also, don't forget to read my paper on the work that began my development of iMDFF, the re-refinement of the insulin receptor extracellular domain.